The data we've measured is shown here in orange. Now I want to convert that into standard units, so that's shown in blue. We're then going to have several trials. For each one we're going to measure the time, calculate the speed, and then the kinetic energy, and then we're going to also calculate the potential energy, and then work out the efficiency. So these are the values I got. Notice they're all very similar. The speed of the car is the distance divided by the time, the kinetic energy is 1/2 mv squared, and the potential energy is just the mass times g times the change in height. The efficiency is just the kinetic energy divided by the potential energy, and we're done. At this point, you might ask yourself a very important question. How come we have almost 102% efficiency? What's going on? Does this show that we've actually proved conservation of energy is wrong? Or perhaps our equations are not quite right? Well, to elaborate on this, allow me to show you what happens if we assume there's a small error in our measurements. So I'm going to change the values that we measured ever so slightly, and this calculation will progress through the error and show you how that affects the final value. I'm only changing one at each time. They're recorded on the left side, and the value it predicts is recorded at the right. Now if you have a look at the first few, these changes don't seem to make much difference. So it's maybe 1% here or there, and that's not a big deal. It might explain why we have 101 though. But check out these guys. If you have even 1 millimeter of difference in the length of the card, or 1/2 millisecond difference in either of the time readings, you get a far bigger error. Since our timer actually only measures to the nearest millisecond, this reveals where this inconsistency has come from. Our data can only really be used to claim that the efficiency is somewhere between 98 and 106%. That means that we cannot claim to have broken conservation of energy. It doesn't prove that conservation of energy is true, but it does say that it's consistent with our measurements so far. Our second question is related to the mass of the trolley. What happens when you change it? Now, we had a mathematical derivation that suggests it wouldn't matter. And also, if you look at the results from before, you can actually see that in those calculations it didn't make any difference either. But let's see what happens for real. First of all, a bigger ramp will be handy, so let's do this. Now there are two different ways we might try and increase the height of the car. The first is to release the car from the top of the ramp each time, but make the total height of the ramp bigger and bigger. The second is to fix the height of the ramp, but release the car from different starting points. I've chosen the second option. Now there's nothing wrong with the first one. Have a look, we can definitely increase the height of the car. But if you take a look at the light gate, you can maybe see that it's actually in the wrong position now. We're going to have to adjust that, otherwise the car is going to hit it. And that will mean that for every single reading we take, we're going to have to record the height at the gate. And this is quite annoying and it's going to take longer, so I'm not going to do that. The constant measurements that we took for the experiment are shown here in orange, and in blue I'm going to convert them into standard units, so mass in kilograms, distances in meters, etc. For the potential energy we have the start and final height, calculate the change in height, and then the potential energy. The starting height was 9.5 centimeters, and I decided to go up in 5 centimeter intervals. To calculate the change in height, it's just one minus the other, then divide by 100 to convert to meters. And finally, we can calculate the potential energy from mgh. The remaining columns are the time we measure, the speed the car was going, the kinetic energy it must have had, and finally, the percentage efficiency. So this is the data I measured. Notice how most values are very, very similar. To calculate the speed, we just do distance divided by that time. Kinetic energy is 1/2 mv squared. And finally, to work out the percentage efficiency, we just take the kinetic energy divided by the potential and multiply it by 100 to make them a percentage. Once again, you might notice that our experiment is very efficient. Two of the values are actually really high, 113%. We'll come back to them. But first, let's have a look at the standard errors we were talking about before. So I've copied the data down below, and what I'm going to do is I'm going to add 1 millisecond and subtract 1 millisecond to each of those times. That will give us a range. It will tell us what the minimum possible time could have been and the maximum possible time. We can then use this with the rest of the calculation to see what the maximum and minimum efficiencies would be as a result of that uncertainty. The blue ones are the lower limits, the red ones are the upper limits, and the green ones are the values from before. So for each green value, we have a sort of range around it where we could have actually measured it if we had been a bit more careful. Now the first three look really nice, have a look, but the last two are actually still a bit off, but we'll come back to them. Now rather than just looking at numbers, what we could do is plot it. So I've copied the data up to the top and plotted a graph of that information as shown. If we put in some lines, you can actually get an idea what the range would look like. Even accounting for this uncertainty, if you have a look at the last 2 points, they're still above the 100% efficiency mark, so there's something obviously wrong. Now there are other uncertainties I've ignored, but this seems to be something else. So I actually went back and reviewed the footage of my experiment, and I noticed something. It actually took me 2 attempts to get the 4th measurement, because the first time I actually hit the light gate with the car. Now this isn't really a problem because you can just readjust it and repeat, but I made a mistake. I didn't remeasure the height of the light gate. I didn't check to make sure it was in the correct position. I just continued as normal. Look, there I go. Close examination of the video suggests that the light gate was actually put in a lower position when it was returned. Now I can't really measure how much that was, but I'm going to assume it was 2 centimeters. This is hardly ideal science, but have a look at what happens if you put this into the spreadsheet. The actual value is roughly constant across the whole range of the height. I have one final bonus for you. In the table I have just actually worked out what the error is for each data point, and I'm going to show you how we would normally plot that in a graph. So error bars are how we show how certain we are about our values, and they're basically little lines. For the uncertainty in the y direction, it's just these values that we've been talking about so far. And in the x direction, it depends on how good our ruler was at measuring the height, and that's plus or minus 1/2 centimeter. This result, to me, would suggest that the amount of energy being conserved is roughly constant. The other thing it shows us is that towards the higher heights, the uncertainty is much bigger, and this is because we're measuring a faster speed at the bottom of the ramp.